So hello Year 8 and welcome back. I'm afraid you've got me again after a couple of weeks with Miss Richardson. So we're moving into a 2-week project. As I'm sure you know, in every topic at Key Stage 3 we've put in a project for you to look at. And this is so that you can practice those skills like writing methods, planning experiments, looking for sources of error that the national curriculum demands that you engage with. So, as usual, this project is going to test how well you can approach a scientific investigation, the how science works part of this. And in particular, this project is going to get you to plan your own experiment, and that will test some ideas that possibly you haven't done, maybe ever, with us at secondary school, which is planning your own experiment. So the Limestone Project Part 1, Planning. Just a reminder before we get on to that, word equations. So you might have seen this slide before, and a word equation is used to describe the chemical reactions. We always put the reactants before the arrow, and we always put the products, the things that are made in the chemical reaction, after the arrow. This is one specific example of a reaction between an acid, hydrochloric acid, and an alkali, sodium hydroxide. And it makes a salt, which in this case is sodium chloride, and water. So the general equation, and you've seen this before, is that an acid plus an alkali makes a salt plus water. And you need to know this general reaction. You need to know that an acid plus a base makes a salt and water. So that if you are given any acid and any base, you can work out what the products would be. So have a think. What are the products when hydrochloric acid reacts with sodium hydroxide? It was on the last slide. Sodium chloride and water. How do you know what the salt is called? Well, you get the name of the salt from the acid and the alkali. So sulfuric acid makes sulfates, nitric acid makes nitrates, phosphoric acid makes phosphates. From the alkali part, sodium hydroxide makes a sodium salt, potassium hydroxide makes a potassium salt, and lithium hydroxide makes a lithium salt, and calcium hydroxide makes a calcium salt. So if we reacted, for example, nitric acid plus potassium hydroxide, then we could work out that the salt, well, it's nitric acid, so it's going to be a nitrate. It's a potassium alkali, so it's going to be potassium nitrate. But we've got to remember it also makes water. You've encountered another example of a general equation. You know that an acid and a metal makes a salt and hydrogen. And we name the salt in exactly the same way that we named the salts on the previous slide. So nitric acid and iron, for example, well, we've got iron, so it's going to make an iron salt. Nitric acid makes nitrates and hydrogen. So, acid and an alkali makes what? Acid and an insoluble base makes what? Acid and a metal makes what? Acid and a metal carbonate makes what? Do you know? Well, do you know the difference between an alkali and an insoluble base? At your level, alkalis are mostly metal hydroxides. So metal hydroxides are soluble they dissolve in water, we call them alkalis. Metal oxides are usually insoluble. We call them insoluble bases. Both of these are bases. An acid and an alkali makes a salt and water. An acid and an insoluble base makes a salt and water. So acid and base, salt and water. Doesn't matter whether they're an alkali or an insoluble base. Doesn't matter whether they're a metal hydroxide or a metal oxide. They make a salt and water. Acid and metal makes a salt and hydrogen. But what does an acid and a metal carbonate make? You may have come across this before, and you may be screaming it at the screen. It makes a salt plus water plus carbon dioxide. So 3 products when an acid reacts with a metal carbonate. Here's a slide for you to ponder and have a think about. Each of these boxes is a missing chemical. So zinc plus sulfuric acid makes what and what? Nitric acid and calcium carbonate makes 3 things. What are they called? Moving down, question 8, what 2 things would make zinc sulfate plus water plus carbon dioxide? And so on. Pause the video, what goes in the boxes? Then restart the video and see if you were right. Okay, so we've got a metal here. So we know a metal and an acid forms a salt plus hydrogen. The salt is going to be called zinc sulfate. Did you get that right? An acid and a carbonate makes a salt plus water plus carbon dioxide. What do we call the salt? Well, it's nitric acid, so it's going to be a nitrate, and we've got calcium. So the salt is going to be calcium nitrate. Did you get those 3 correct? Potassium hydroxide and sulfuric acid. This is a base and an acid, makes a salt and water. What do we call the salt? Potassium something. Sulfuric acid makes sulfates, so potassium sulfate. Nitric acid and calcium oxide. Calcium oxide is a base, so acid and base makes salt and water. What do we call the salt? Calcium nitrate. We've got a carbonate here. Acid and carbonate makes a salt plus water plus carbon dioxide. Notice I'm not writing CO2. This is a word equation. We have to write the full words. What do we call the salt? It's going to be iron something. Hydrochloric acid is our special case. It makes iron chloride. Have you got all these right so far? If so, fine. If not, pause now and check the rest of your answers. Okay, now we're asked to go the other way round. We're making hydrogen, so we must have a metal. The metal is calcium. Not a metal oxide, not a metal hydroxide, not a metal carbonate, just a metal because we're making hydrogen. Nitrate comes from nitric acid. Lead sulfate here. Well, that clearly comes from sulfuric acid. Now, we're making water and just water as the other product. So it's got to be a base. It's got lead in it. So we've got two options. It could have been lead oxide. It could have been lead hydroxide. Either one of those is fine. I'm going to make it clear it's either, not both. It's lead oxide or lead hydroxide. Right, we're making carbon dioxide here, so we know it's a carbonate. We've got zinc, so it must be zinc carbonate. We're making a sulfate, so it must be sulfuric acid. Question 9, we're making hydrogen, so it's got to be a metal. What's the metal? The metal is lithium. Not an oxide, not a hydroxide, not a carbonate, the pure metal, because we're making hydrogen. We're making a chloride, so what's the acid? Hydrochloric acid. Calcium carbonate plus what gives calcium chloride plus what plus what? It's a carbonate. Salt plus water plus carbon dioxide. We're making a chloride. What's the acid? Hydrochloric acid. Tin oxide plus what makes tin chloride plus what? It's an oxide, it's a base, it makes a salt and water. So chloride, for the third time in a row, hydrochloric acid. We made a nitrate in question 12. That comes from nitric acid. We've got an alkali here. Alkaline acid makes a salt, which is here calcium nitrate plus water. That is the missing answer there. Sulfuric acid plus barium hydroxide. Acid and alkali makes a salt plus water. What do we call the salt? Well, it's barium, and it's got sulfuric acid, barium sulfate. Finally, what, or almost penultimate question, question 14, what plus citric acid makes magnesium citrate and hydrogen? Well, to make hydrogen we need a pure metal. That metal must be magnesium. And finally, phosphoric acid plus what makes potassium phosphate and water? It must be a base. It could be potassium oxide, or it could be potassium hydroxide. How did you do? Did you get most of those right? If so, well done. If not, you need to go back and check you can do these. Now, for the main part of this lesson, limestone. As Dr. Butterworth wants to tell us, limestone comes from the Latin lime, meaning a sort of gluey slime, stone, icicle. So limestone is sort of like a slime icicle. Where did it come from? Well, it mostly comes from sea creatures. So mollusk shells, corals, fish, they're made from calcium carbonate. Calcium carbonate has the formula for those that are interested, CaCO3, calcium carbon oxygen. And that can get turned into limestone. But how did they turn into limestone? Well, we're going to do a whole topic after this one on the formation of rocks and how rocks form and how they are interconverted. But basically, all of these dead corals and mollusks and fish die and they fall to the bottom of the seabed and they form a layer on the bottom of the seabed along with bits of rock that have been ground up and blown in or washed in. And over time, more and more layers build up on top of these dead sea creatures, and that forms a compacted sediment which over millions and millions of years will turn into rock because of the pressure from above. And as I said, we'll do this in far more detail next topic. So limestone is made up not just of calcium carbonate, which comes from the sea creatures, but also it contains things like silica, clay, silt and sand. So these come from ground rocks or ground up rocks. These come from the sea creatures. And they both get smushed together into your limestone rock. If something contains lots of sea creatures, so this is mostly seashells, etc. So this has lots of carbonate. If it contains those bits of clay and other bits of rock, this has not so much carbonate. But we may want to be a bit more quantitative about that. So here's the practical. We've got 3 different types of limestone. We've got one that's come from Jeffersonville in the good old US of A. We've got one that comes from the Cotswolds in the good old UK. And we've got one that comes from Tamala in good old Oz. And we want to know which one contains the highest proportion of calcium carbonate. Design and carry out an experiment to determine which sample of limestone contains the most carbonate. That's what you are going to investigate. So this is the key thing. Can you research methods for finding out how much carbonate is in a sample of limestone or a sample of rock? What I want you to do is do your research, and then I need you to complete these bits. So this is complete today. So here's the planning grid that you've got to fill in this lesson. Firstly, what's the independent variable? What are you actually going to change in this experiment? Secondly, what is your dependent variable? What will you find out? What will you actually measure? You're not actually going to measure the amount of calcium carbonate in each limestone. But what are you actually going to measure in your experiment? What are your control variables? What do you need to keep the same? How do you make sure it is a fair test? Then, what is your method? Remember, it needs to be step by step. Set up the apparatus as shown in the diagram below. Add 50 centimeters cubed of, I don't know, something acid to a what, you know, ... Then step 3, what are you going to do next? Keep it specific. If I gave your method to a year 8 in another class, could they do your investigation? That's what you need to think about. Then we need a scientific diagram, not a picture. It should be 2D. It should be labelled. It should be drawn with a pencil and ruler, showing how you set up your experiment. Just to show you what I mean, because I think some of you really don't know how to draw a proper scientific diagram, I'll show you with some actual examples from 8 AM over the last couple of weeks. So this is what we don't want. We don't want a shopping list. We don't want a picture of all the things that you will be using during your experiment, as though you were sending someone off to go shopping. And here's another example of that. We also don't want you to try and draw a lovely three-dimensional picture of what's going on. So here this person has attempted to draw the beaker being put on the tripod over the Bunsen burner, but this is not how we do scientific diagrams. This is a really good example of a scientific diagram. We've got a nice labelled diagram drawn with a ruler, pointing out the key features and how they're put together. Yes, some things are labelled incorrectly. The mesh is a gauze, the stand is a tripod, and it's not drawn in pencil. But this is a really good diagram. This is also a really good diagram here. Fully labelled, the Bunsen burner has been simplified. But the one I really love is this one. Because although this hasn't been drawn with a ruler, the person, the author of this picture, has realised that actually we don't need to know what a Bunsen burner looks like. We just need heat. So do remember your key scientific diagrams. This shows you that every piece of apparatus should be drawn as a cross-section in 2 dimensions. So look at the beaker. This is a picture of a beaker. When we draw it in reality, look, open top. Because if we cut through a beaker and we sliced it in half, well, what would we see? We would actually see a cross-section that looked like that. A tripod, here we go. If we cut it down the middle, we would end up with something simple that looked like that. The gauze is just this dashed line here, because that's what it would look like if we cut in half. An evaporating basin, drawn like that. Filter paper and filter funnel, drawn like that. And this is how I want you to draw every scientific diagram from now on, and in particular your scientific diagrams for your method this week. And finally, for this first part, here's the first hazard and the first clue. Corrosive acids getting in your eyes. If you're struggling to think of a method, it's going to involve acid. The risk is high. The precaution is to wear safety goggles. I want 1, 2, 3 further hazards. What are the risks of each? And what precautions are you going to take? When you've completed that sheet, you can either do it electronically or you can write it. You need to submit it to me on Google Classroom. Over to you.